All right. Thank you, everybody, for attending. Wonderful to have you back. And sorry to those who my poor advertising caused to miss this lecture and who are hopefully now watching this on Zoom or on YouTube. We had to reschedule things because there was a symposium on Friday, and so I had to give a talk, and so it got rescheduled today. Today we will be talking about affine schemes, the spectrum of a ring, and then associated properties of the spectrum of a ring. So we're basically going through chapter 3 of Vakil's book, The Rise at Sea. So if you want to follow along, or if you're interested in doing exercises to accompany these lectures, that's a good place to start. So last lecture, we talked about wanting the relationship between affine varieties and ideals to be a bijective correspondence, and we presented the classical method of accomplishing this, which was the radical ideal. But then we introduced sheaves as a way to get kind of the modern algebraic geometry approach of schemes, which would allow us to enlarge the set of affine subvarieties to match up with the set of ideals of a polynomial ring with n generators. So today what we're going to do is we're going to talk about affine schemes, and we'll make this definition somewhat exact. So there's 3 components to affine schemes that are kind of the data of the scheme. So are these visible, by the way, on the far side?
Yeah, overview, schemes, the set, spec R.
So yeah, in this overview section, there's 3 pieces of the scheme, which are the set, the topology, and then the structure sheet. And so the idea is the set of a scheme is this thing, spec R, and then next lecture we'll talk about the topology and the structure sheet as induced by the topology. So as a definition of the set of an affine scheme, we'll define spec R to be the classes of ideals P contained in R such that P is a prime ideal of R. And we'll recall, just for undergraduates tuning in, that an ideal I contained in R is prime if and only if the product AB in I implies that A or B is in P, or is in I, sorry, for all A and P. There's a lot of equivalent ways to state this that are traditional theorems from abstract algebra 2. We'll see that one of the ones that we'll like to use is that if an element is up to some notion of divisibility irreducible, then, assuming that you have a division algebra, then this gives you a prime ideal. Like if the generator is irreducible. So this is kind of something to start chewing on in terms of the connection between varieties and schemes. Okay, so in terms of the definition of spec R, we have a few sub-definitions that are really crucial, and then I have some examples for, because it's very counterintuitive and easy to get lost at first. So elements A in R are called functions on spec R. And then the value at a point, so points are elements of the scheme. The value of a function A at a point P, so of a function A at a point P.
Sorry, can I ask a question?
Yeah.
Yeah, you're using square brackets. Is that an equivalence class, or you just mean prime ideals, like in your definition of spec R?
Yeah, so this is an equivalence class. It's an equivalence class that we'll talk about.
Okay.
And so, yeah, we'll talk about that in a little bit. We'll get more into the depth of it when we talk about the topology, but yeah. Okay, so the value of a function at a point in the scheme is, and I guess maybe I'm just going to underline that so that we know its function is going to be a mod p. Okay, so as an introductory example, we'll consider spec Z.
So by A mod P, do you mean the element in R mod P?
Yes.
The image in R mod P?
Yes.
Okay.
Yeah. You can view this very much as a coset sort of thing. Since we're working with polynomials in general, it's easier to just think of it as the Euclidean division algorithm on polynomial functions. But yeah, this is an element of the quotient ring R mod P. And this is sort of where this comes from. Okay, so spec Z. I'm going to make a claim that this is really the set of ideals P, such that P is prime. And this is a prime integer, right? This is something that you can justify. This is something that Vakil actually goes through in the book. So because it's included in the book, I figured I wouldn't go through it. But suffice it to say that this is the set of prime ideals of Z. So we can consider something like the function of 5 in Z, evaluated at a point, P spec Z. Well, for varying P, we get different results. And so we see that a function can take on different values in different rings at different points. So like if we replace P with 2, for example, then this is 1. And if we replace it with 3, then this is congruent to 2. So this is kind of our first notion of functions on schemes, and kind of like an example to always come back to remember how, like, which side of things the division algorithm is, and which one is really a function, and which one isn't when we're working with polynomials, is this example. So I don't know, it's just like a helpful tool. Okay, so in this way, we see that an element of the ring, which is really a function, so an element of the ring lying in a prime ideal translates to a function that is 0 at that ideal in this scheme. So I'm going to actually, this is kind of a key notion of what we're doing here, so I'm going to write this in text. Okay, so the idea is so A in R with A in P in spec R is equivalent to saying that the function A vanishes at P scheme theoretically. And we'll kind of say this usually is like a function vanishing at the point is determined by inclusion in the ideal.
Tim, what is you have something dash slash A in P? Is that?
Wait, sorry, it's a W.
Oh, W. Okay, got it.
I always forget that I need to write larger than I do.
It's all good.
Thank you. Yeah, if I ever write something too small, please point that out to me. Okay, So we'll notice a few properties of functions of schemes. So if we have f and g are functions in the ring R, we know that, or we see that f plus g, f plus g at some point so is equal to f evaluated at the point plus g evaluated at the point. And then the same thing works for a multiplication. So f times g evaluated at p is equal to f of point times g evaluated at the point. So this is a translation of the property that the map from R to the quotient of the ideal is a ring morphism, which is why I won't prove this because this is a valid ring morphism. So anyway, but in terms of useful properties of schemes, this is certainly one. Okay, so as an example, this will be one of our main examples for the rest of the course. We'll consider affine one space over the complex numbers, which we will define to be spec C over X. So the prime ideals of the polynomial ring over an algebraic closure correspond to irreducible polynomials over C. And so this is the set of the form stuff that looks like x minus a, ideal-wise, and then the ideal of 0, and that's its own special case that we'll talk about at the end. So initial things that we'll note about this scheme, since we'll be working with it primarily for the rest of this seminar, is that we have, for each traditional point of the complex numbers, we have a traditional point scheme corresponding to x minus a. So for each linear factor, this works well. We also have the 0 thing kind of floating around on its own. And the idea is that, well, 0 is really contained in every single ideal here, and so geometrically we're picturing this as this thing that kind of like goes through every single subscheme of this scheme. And we'll call this the generic point, and we'll elaborate on this at the end of today's lecture or at the start of the next lecture. Okay, so going back to this example of functions and schemes evaluated at points. So if we consider something like f of x is equal to x squared minus 1, g of x is equal to x cubed minus 1, and we consider the point P is the ideal generated by x minus a, right, of course, for any a. In C, well, we have f of x plus g of x mod x minus a ends up being, I guess we can work through this. Yeah, this works out. So x squared, or x cubed plus x squared minus 2 x minus a. And then dividing out by x minus a, we can say that, well, x cubed plus x squared minus 2 is equal to something times x minus a, and we'll kill off the leading term. So x squared plus a remainder. Well, this is x cubed minus ax squared And so we have, this is equal, so we need a plus 1 copies of x squared. And then we need minus 2. Okay, and so then now we have that x squared is equal to a plus 1 x squared minus 2 times something plus a remainder. If we follow this through the Euclidean algorithm, and then the extended Euclidean algorithm, we'll end up getting that the result of this division is going to be a cubed plus a squared minus 2. And so this is kind of the strong idea. And something similar can be verified for a product of these polynomials. So we have kind of this relationship between functions and points in the scheme. And we have that it works nicely with Euclidean division, certainly. And we can see how this can apply to complex algebraic geometry. Okay. And also, yeah, I guess the piece that I'm not doing here is if you evaluate f and g separately, then you get the same answer. Namely, that if you evaluate this at x minus a, you get a squared minus 1 and a cubed minus 1, and then you sum them together, you get the same. Okay, so let's take kind of a picture of our affine schemes. And let's figure out what these things look like, because we want to have a geometric notion of what we're looking at. So the affine line, which we'll define to be A1 of C, like so, is going to look like points that are traditionally complex, and then this kind of weird thing where we have the generic point that I kind of started talking about. So we see, like, on the algebraic side, we have this point, I guess, I'm sorry, on the geometric side we have 0, but on the algebraic side we have the ideal x, and so we can view 0 really as being this class of the point x. Similarly, for any other number like 1, we have x minus 1. And so for x minus a, we also have this. Again, I've talked about the generic point as being this thing that kind of runs through every other ideal because it's contained in it. This is exactly our notion of something being like a generic point, is that it runs through every other ideal. There's some more to talk about. This is not the only type of generic point.
Does every scheme have a generic point?
Every scheme has a generic point, yes. Namely 0. So we like to say that a scheme is reduced if the only generic point is 0. And the idea is that if you were to mod out by all of the generic points, then you would get something isomorphic to the original scheme. And then that would be a reduced scheme. But it would have different polynomial generators in terms of the local arithmetic.
So you can have more than one generic point, but you can reduce it? Is that what you're saying?
Yeah. The idea, and this is something that we'll talk about at the end, is that if you take, and we haven't really talked about localization, but I know that you're familiar with it. If you take the local ring at some point in the scheme, well, then the localization will have nilpotent elements. You'll have elements that have some powers equal to 0. So if you mod out by the no radical, which we talked about last time, the no radical of the scheme is similarly defined, then you get something isomorphic to the original scheme that'll just have slightly different generators that make it reduced at all local rings.
Got it.
We'll also talk about this more next time, which I think is nice because this is like a really important thing about schemes and a really important thing about like why the relationship between affine varieties and ideals is not a bijection. So yeah, that's a really good question. Yes, all schemes have generic points, and we're really interested in the schemes whose only generic point is 0.
Got it.
Okay. So yeah, it's worth noting with the affine line, we're working over the complex plane, but we're drawing this as a line. And the reason for this is that we are really, honest to goodness, thinking of this as a line. Not in the well-ordered sense, but in the sense of this is a one-dimensional space. We haven't yet defined dimension, but you can think of it now in the sense that since this is smooth, the length of this ideal is determined by the degree of the polynomial generated. We'll see later that this is not always the best definition for the dimension of a scheme, but for smooth schemes, this works nicely.
What is it going to be, like the curl dimension or something like that, or?
It will be the curl dimension, and it will be ultimately determined by singular points and points that are non-reduced. So points that have generic points that are non-zero.
Got it.
Yeah. In a sense, if you've seen like the Riemann-Hurwitz formula, like the number of nodes in a curves and the number of poles of the arithmetic genus of a curve determine the dimension of the scheme. So that's kind of jumping up to stuff that's a little too advanced for lecture 5, but we'll get to it eventually. Okay. So towards this notion of spec C over X and affine space, I also want to remark that rational functions are perfectly well defined for this sort of thing. So if we consider f of x is equal to x minus 3 cubed x minus 2, the bottom, well, this is an element really of the open cover of the affine line minus the point. Minus the point x minus 2. And this may seem very simple, but this is actually a very, very deep thing that we're going to talk about later on when we talk about divisors. We'll want to be able to bookkeep all of these things, and we'll see that this is really an element of the structure sheaf, where this is a function assigned to this open set. So when we define the topology on affine schemes, we'll define the Zariski topology again. Open sets are going to be the complements of the vanishings of functions, and then we'll define the ring of functions on those open sets. And we'll see that this f of x is exactly a function defined on this open set. I'll do that in more detail next lecture. I just want to remark that we can have rational functions in here. Okay. Kind of an aside remark that I think is maybe useful, especially for people who have never seen schemes before and want to work out some examples for themselves. A good example to verify that you're getting the hang of this is that the spectrum of any field is boring because it only has one point. And if you haven't ever worked that out, it's worth doing. Similarly, the trivial field has no prime ideals, and so is also boring. So just things kind of to keep in mind. Okay, how am I doing on time? 3:30. There's an example that I think is interesting, but I want to make sure that it's going to leave us time. I think I'll omit it, but the spectrum of a finite field. So spec FP is going to be kind of an interesting case. If you want to read through my notes, they're teched up in the overleaf link that's attached in the description of this video, or either of you, Rebecca has it. Jackson, if you're interested, you can look through my notes. Okay. So I want to talk about localization now, because it turns out to be something very important to understanding the geometry of schemes and how schemes really help us accomplish things geometrically.
Well, so Tim, on your spec FP example, so that'll just be a point, right, that sits inside of spec Z, sort of?
So it's the set of ideals 0, and then f of x, where f is irreducible over fp. Sorry, I meant spec p, or spec fp over x.
I see. That's a much more interesting ring.
This is much more interesting. Very, very good errata. Yeah, this is what I was talking about being interesting, because like I literally just said, the spectrum of a field is boring. So yes, fp over x. Precisely.
So that'll depend on the prime factorization or
Yeah.
factorization of the irreducibles.
And I think, so when I cooked up this example, I thought it was really interesting. In my Galois theory course last year, we did construction of fp by, zp over x mod some polynomial of degree n. And so you get, fp to the n, spec fp to the n. This is a really interesting example. That's what I worked out. I worked out spec f8 of x. So that's kind of like a fun one, especially if you're interested in p-adic stuff, which I know you are.
A little bit.
Yeah, so feel free to look through my notes. It might just be fun for you. Okay, so let's talk about localization. So this is one of those things where I'm kind of kicking myself for not talking about it sooner in the context of varieties, because it would be really convenient to just hop into the machinery of localization by ideals. The big idea is there's some behavior that we would like to restrict about varieties. And when we talked about sheaves and germs and stalks, we would like to be able to think of like shreds of functions around their local neighborhoods. And we would like to be able to think of like kind of complements of that. So the idea of localization is that there's really two types of localization. And if you haven't seen it before, you'll read a textbook and it'll be very confusing for a few minutes until you figure it out. So type 1 localization is if you have like a ring, you can localize it at some multiplicative set, and I'm going to do S inverse on the left times the ring. So S is called a multiplicative set, meaning that all of the elements in S have inverses in the ring. What this can look like quite often is 1f inverse f minus 2 dot to f minus infinity, and often we'll abbreviate this as rf. You can imagine that we can do this with more than one ring element, and so we say localizing, S inverse R if we have a multiplicative set that isn't generated just by one thing. But otherwise, we do it like so. The idea, scheme theoretically, is that we want to go away from the locus of this function. So if f is a function on our scheme, spec R, then f has a vanishing locus in spec R. And we want to stay away from points where division by 0 happens. And so when we multiply through by all of our copies of the f inverses, then what we're doing is we're kind of making this section of the structure sheet, and this is what we'll see next lecture, where f doesn't vanish. So this is kind of our first idea of localization, is localization away from a function. Now, so this is localization at a function. Type 2 localization is localization at an ideal, or really at a point. So localization at a point looks like Ri for some ideal. And so the idea is that, and oh yeah, I guess we'll call this a distinguished open set. So before I get onto this, so a distinguished open set, or does not vanish on F. So this gets abbreviated as like df back R. And Nikhil has this really helpful thing in his book where he says, "Oh, does not vanish at F." That's what the D is for. Okay. Where am I? Yes. Oh, let me actually compute an example of this before I move on. because I have it written down and because it's helpful. So example of type 1, we'll take our affine space, our affine 2 space, which is spec C over xy, and we're going to localize this at function y minus x squared. And so geometrically, we want to picture this as the affine plane minus points lying on the parabola defined by y equals x squared. And scheme theoretically, we're going to see that there's an interesting stratification happening of our scheme. So A2 localized F is going to look like all of the things, all the prime ideals points away from y minus x squared, and then the generic point. But what this is going to consist of are two types of points. So we're going to have maximal ideals, x minus a, y minus b, corresponding to points in the complex plane that are not on the parabola. But then we're also going to have a dimension 1 point that's the vanishing y minus x squared. And so I guess really the point here is A, B, and C. So what we have is we have a dimension 1 thing, but then we also have a dimension 2 thing determined effectively by the degree of polynomial. Again, dimension is this kind of weird thing that we're working with, but I want to be focused on the fact that there is some sort of affine stratification happening determined by the localization around a curve. So affine stratification becomes really important later on in algebraic geometry when we want to think about intersection theory. And localization is often an easy way to get an affine stratification in the scheme. So, food for thought.
So what is the localization of this ring? Did you wrote down this, I guess, variety A2F consisting of these ideals, but do we know what the localization is?
This is the localization.
Oh, that is, okay.
Yeah. So A2F is the localization. I guess really, you're right. I've kind of made this confused notation. So it's AC2 localized F is how you would see this in like a paper or a book. So yeah, I just kind of omitted the C. We're not working over finite fields for the most part, so we're going to omit the subscript from now on of the complex numbers, simply because it's convenient. And so if I ever write F in here, it's usually going to mean a localization, but please feel free to ask.
Okay. But would the ring, the localized ring itself, would that be C of xy modulo that ideal, or? No, right?
No.
Okay.
So that would be something different.
Okay.
Yeah. Okay. So type 2 localization is localization at 90. So along smooth curves, this first type of localization is just fine. But what happens along something that's singular, like in the real plane, two axes, so the ideal x and the ideal y, respectively, well, at this point we have xy. And so if we take something that looks like C, we call this capital X, which is spec C xy mod the ideal xy, we have something that is a generic zero divisor at xy. So if we consider the localization at x, then what we're doing is we're throwing out the locus where x vanishes. And so we want to consider just the x-axis and then minus the origin. So the y piece goes away, the origin goes away, and then we're left with just the x-axis minus the origin. And so then this ends up being spec cx mod x. I'm realizing now that I wrote that transition very dramatically like a transition from localization type 1 into localization type 2. It doesn't do that. This is just a good thing to know. I am going to transition out to the second type of localization now that we know how to localize along certain types of singular groups, or at least have an example of it. Is this a clear example at least?
Yeah. Hold on. C of x mod x, is that just the complex numbers, or am I missing something?
You're right. This is not.
Yeah, that looks like a point to me.
Yeah, it's this localized at x.
Okay.
It's a very, very good point. Thank you. Yeah, and it's not the ideal x. It's actually just the function. So I read that wrong twice. Okay, now it's correct, I think.
Yeah, it looks better.
Yeah, this looks fine. Okay. Any other? Okay. So our other example. Yeah, so our localization of a prime ideal, where so I guess I'm going to replace I here with P, where P is in spec R, is traditionally denoted either P inverse X or XP. This is going to consist of elements with denominators in P. So this is going to be I inspect R, where I has denominators and we want to think of this as the set of prime ideals which fail to meet the multiplicative set P. Yeah. No, this is still localization at a point of the spectrum. I'm going to post an errata, I think, in the comments. So this is still localization at a point. And I guess in the same sense that, no. Okay, this actually does work out. My apologies for the confusion. I wrote these notes like a week ago, and so I'm having to read what I did a week ago. Okay, so the idea up here is if we localize in our multiplicative set in the ring, then we can push to the localization of the scheme, and this looks like localizing maybe at an ideal. And so then if we localize at a point in the scheme, then we're localizing at prime ideal. And that's what this looks like. So you can localize the ring at an ideal, or you can localize the scheme at a point. And geometrically, they'll look somewhat similar, even if the output looks different. Okay.
I'm not sure what you have there makes sense as it is, because denominators in P, like that's not necessarily going to be an element of spec R. That's going to be an element of spec R that's going to be an element of, you have to invert all the things in P first. So what you have just doesn't quite make sense. Like R doesn't have denominators.
Yeah. Yeah, I'm with you. This is a poor definition. So I will give the geometric motivation for this, and in the comments of this video, I will post an errata with a timestamp with the proper definition of what this should be. And yeah, so okay, this works somewhat like the distinguished open set intuition that I was talking about. So intuition this is going to be points of spec R, which fail to mean P. And what we're really saying then is that, and I think maybe I won't have to post the errata if I get this right on the first try, is that if we have I in spec R, where I does not contain E. That is the proper definition. Okay. No errata necessary, we fixed it on the spot. That never happens. Wonderful. Okay. So yeah, this is Tech 1 and sort of Tech 2 localization. Now, I'm going to give some more examples of localization, just to build some intuition, because clearly it's needed.
So is type 2 localization, you mean like localizing a ring at a prime ideal? Is that
Yes.
what you're getting at? Okay.
Okay, so consider the multiplicative set of a scheme minus, like set minus a prime ideal. Then we want to, oh boy, nope. We're going to make X R and we're going to make R a ring. That's pretty important. But R minus an ideal. And then we're going to consider spec S inverse R. All right, so then these are the prime ideals of X contained in P. So this is the I in I subset, and I in spec R, such that I is contained. Let's see. In the example with R equals, I guess the example C going xy and P equal to the ideal x comma y, then we keep all points corresponding to things near the origin. So if we let S be C xy minus the ideal xy, then R, S inverse R, the scheme, is going to look like all of the things near the, all of the things near the origin. So the zero-dimensional point xy, and then the two-dimensional point 0, and then all of the functions f of x such that f of 0, 0 is equal to 0. This is actually kind of the crucial example of this. So the picture morally is going to be, we'll have types of curves that vanish at the origin. And then we'll have curves that maybe go around it or something, but don't like vanish at 0. And so this is kind of going to be our notion of the shred of curves that vanish at 0 on, affine 2 space. So this is going to look kind of like the stalk at 0, 0, stalk at the origin. And that's our sheaf theoretic notion for this. Okay. Are there any questions about this example? Okay. So
Where are your things that go around the origin
what do you mean?
in your list?
Things that go around the origin don't make it in here.
Ah, okay.
Yeah. So it has to vanish at the origin.
Yeah, yeah. I wasn't sure why you were putting the things that go around the origin in there.
Yeah. I think maybe it's unclear. Maybe it's just in the video. This is an S.
Okay.
Yeah.
Yeah.
So this is a localization into the set.
Yeah, yeah. No.
But yeah, that's definitely a valuable question if that wasn't clear, because that's why I'm showing this one. Okay. So real fast, unless there are any more questions, I'm going to talk about maps of spectra. And how they behave with localization, if time permits. So we're going to talk about morphisms of spectra of rings, which will become morphisms of schemes once we endow a topology, the Zariski topology, on our affine schemes. So kind of a theorem, it isn't super hard to prove, and it's proven in Bakil, is that maps of rings induce maps of spectra. So if we have map phi from B to A as a map of rings, then we induce, I guess maybe I'll draw this differently. Phi from B to A induces a map spec A to spec B. So namely, phi inverse of P, which is an ideal, where P is an ideal of B, no, A, is going to be a prime ideal B. So, spec A. So you can pick a prime ideal of A, and it's going to have an inverse image, which is also prime in B. This is going to be our basis for building continuous maps under the Zariski topology on affine schemes. So then considering this as a functor from rings to spectra, we are rings to sets, really, because we haven't endowed with topology. We have a contravariant functor from rings to sets. Namely, we induce a pullback on spectrum by star. Okay. I think that this is a good spot to end it. I have some notes in here that I definitely don't have time to do thoroughly and may cause more confusion if I do them in a short amount of time. I recommend looking at them and working through the notes at the very end of lecture 5. If there are any questions from people on YouTube watching this later, please feel free to text me or write in the comments a question with the timestamp. So, okay, thank you so much for your attention. Are there any questions before we end the lecture? Yes, Rebecca? Oh, no? Okay, just waiting. I see. Okay.
No questions for me. Nice
Okay,
job.
I'm going to end the recording.
All right.